Today's topic is heaps. Okay, so what is heap? It is basically a complete binary tree, all levels completely filled except possibly the last, and the last level has all keys as left as possible. Okay, let's see one example of the binary tree. So it should have two child, left and right, correct? Left and right. This is the example of binary tree, correct? Now heap is a complete binary tree, means every node should have all levels completed, right? So left and right child should be there except the last. Okay, we can accept the last, and the last level can have the all keys as left as possible, right? So this is the example of complete binary tree, and heap is the complete binary tree. So we can say this is heap. Now there are some properties of heap, okay, which satisfy the heap properties. What are the properties? These are the properties. Shape, it should be complete binary tree. This is the example. And order, now this is important. Parent node is smaller in the min heap or larger in the max heap, correct? So if you see some example, let's take this example. Okay, we are given array 1, 3, 6, 5, 9 and 8, right? So what should be the min heap? Min heap can be this one, right? It has the root node as smaller, that is 1, and left and right are greater than the root the parent node, correct? So this is the example of min heap. You can also see this tree, the subtree. In this also the parent node is having the value less than the children, correct? And what is the property of max heap? Vice versa, correct? The reverse order will be the max heap. Greater should be the root node. The parent node should be greater than the child node, that is 9 and 8. Okay, and we can write it in array form, right? So 1, 3, 6, 5, 8, 10, 9, 6, 3, 2, right? So this is the example of heap, both min and max. Now this is important, right? While implementing the heap, let's say we are implementing the heap, the custom heap, in that we will be using array, and these indexes are important. Let's say we have index for this root, let's say this is I, this is I. Okay, now what is the index of left child? It will be 2 into I plus 1. How? You can check in this array. See, for 1 it's 0. Now for 3 it's 2 into 0 plus 1, right? So it will be 3, and for right it will be plus 1, so plus 2 will be right. Got it? Let's say if we are checking this subtree, this will be I. Now what is the index of this? It should be 2 into I plus 1. Let's verify this. So it's 1 into 2, 2 plus 1, 3. Yes, it's correct. And for the right it will be 2 into I plus 2, correct? So let's say if we are given the index of this node I, we need to find the index of its parent. So this is the formula, I minus 1 divided by 2. Okay, so time for insertion and deletion, it will be log n. Okay, so log n is the time complexity of insertion and deletion, right? So how? Basically there is a function or a term that is called heapify. What is heapify? It is basically the operation to maintain the heap structure. What is the structure? It's complete binary tree, correct? And for the max heap, the parent should be the larger, and for min heap it should be the smaller parent node. So these are the structures. Okay, correct? So these are the structures for min and max heap, and we need to maintain this. right, while inserting the new elements or removing the element, correct? This is min heap, this is max heap. These are the structures, correct? Now heapify is the function. Okay, so let's say, let me 1 3 6 5. Okay, let's say this is the given current, we can say current heap or data, let's say. Okay, now we are adding one more element. Let's say we are adding what? Let's say we are adding 9, or let's say we are adding 2. Okay, we are adding 2. Now, is the structure maintained? Is the order maintained for min heap? No, right? So we need to maintain it. Here we will be using heapify. So heapify what? Up. Heapify up. And what is heapify up? Basically it will compare. See, this 2, it will compare with this, the last known leaf node. Okay, it will compare with this. This is smaller. Yes, this is smaller. So it will swap. Now 2 will come here, 3 will come here. Again it will compare with its parent. Now is the order maintained? Yes, it's maintained. So we can say this is the structure, right? This is heapify up. We are starting from the leaf node, okay, the last node, to root. Okay, understood? And we will be using these indexes, right? And let's say, and this is the code for heapify up. Okay, so while I is greater than 0 and we are comparing with the parent node, right? This is the index for parent node. You can see here, right? You can see here, this is the code, this is the index for parent node. We are comparing with parent, and if it's smaller, the new node, we can swap this, right? Correct? So this is the code for heapify up, in the sense of it will replace the leaf node to the root node with the minimum value and vice versa. Correct. This is what? Heapify up, right? Now this is for insertion. When we are inserting the new element, let's say we are removing, from where we should remove? We should remove from the front only, right? Let's say we are having what? 1 2 6 5 and 3. Let's say now we are removing from the front. It will obviously remove from the top element, right? In the priority queue also. So we removed this element, correct? Now we need to maintain the order. How it will do? It will take this element, the rightmost element, the least and the rightmost element, that means the last element, and we will place it at the top. We place it at the top. Okay, now we need to maintain the order, right? Maintain the order. We will apply heapify. In this case it will be down. Okay, in this case it will be down. Now what we need to do here? See, we will take this element and the children, we will compare them. They both are same, or which is greater? 3 is greater, right? But the property says parent should be smaller, so we will swap them. 2 and 3, correct? Now it will compare again with the children. Now it's maintained, it's correct. So this is what? This is heapify down, and we will apply this while removing. And this is the code for heapify down, correct? We are having the parent, the root, right? The smallest, let's say initially it was 3 and 2, right? Now smallest will be this 3, left will be what? This 2, and right will be 6. Correct? We are using the indexes and we are getting the elements. Okay, now we will compare. We will get the smallest among these three. We will get the smallest among these three, that is the parent, the left and the right. The left, right and smallest. Correct? After that, we will swap the smallest with this, with the root element, the parent element, and we will do same again, right, with this, with next subtree. Correct? So this is the code for heapify down. Now the time complexity of this up and down will be, what is the height of this tree? Let's say we are having n elements. What is the height of this tree, the depth? It will be log n, right? So maximum operation can be log n only, right? One side of tree. So in that way, both the operations can take up to log n time complexity. Heapify up and down. Got it? While inserting, we will do like this, heapify up, and while removing, we will do like this. So these are basically the offer. Like let's say here, this is the priority queue. We are using priority queue, the min heap, and we are adding the element. So in this, it will be using heapify up operation, right? All offer. Correct? And here we are removing the element, so it will use heapify down. Correct? So it will take log n time complexity, both insertion and removal. So this is the heaps, the priority queue, right? Now see, this is the example of simple min heap, right? Now if we want to use max heap, how can we use? So in here we will use this thing. Correct? Now this is what? This will be max heap, because we reverse the order. Got it? And these basic operations, offer, this pool, right, peak, these will be the basic operations, same as queue. Correct? And these are the basic definitions we did earlier also. Min heap, the parent is less than or equal to its child, the smallest element is the root, and here max heap is greater than or equal to its child, the largest element is at the root. Now the use cases where we can apply the heaps. Where? Priority queue. Heaps is used to implement priority queue, right? This is the example, and I explained the insertion and the removal part, right? If we want to find the top k elements, we will use priority queue, like min heap or max heap we can use, right? As we did in the last session, top largest kth element, right? So heap sort, in the heap sort also we will be using in place sorting using heap. Median of stream min heap plus max heap combo to maintain the running median. Dijkstrata algorithm, this is important for finding the shortest path, right? So here we will be using priority queue, right? This is the graph, important theory or the part. Merge case ordered list, this we will cover tomorrow, right? So these are some use cases and how to apply. Simply we can use the priority queue, that's it. You can apply them heap when you need to find the frequent access to the min or the max value, like we are finding the shortest path. In that case we will be needing the shortest path till now in every traversal, right? So there we will be using this heaps. You need to maintain a dynamic set of elements where you perform insertion plus deletion, like priority queue. Okay, priority queue. Correct. You need to solve top k elements, smallest k, largest k problems. In that we will simply use priority queue. the min or the max heap accordingly, and priority based processing, correct. So there will be some questions like scheduling with the priority, right? Scheduling meetings with the priority. So some questions like that. And these are the implementation. For the min heap, you can use simply new priority queue, and for max heap you will be using collection dot reverse order. And we can also use like manually our custom comparator. I will show you in the question here. Okay, benefits: fast access, O1 access to min and the max value, it will be at the top, right? Efficient update, login, it will take login time complexity in insertion and the deletion part. Dynamic, adapts to the changes in the dataset. Okay, memory efficient. So these are some benefits. Example, these are the examples of the question. I will give you the list of questions at the last. Okay, so today's first question is top k elements. Here we need to find the top k frequent elements. Okay, frequent elements top k, right? So again we need to maintain a window of size k, but we need to maintain with their frequencies, right? Because frequent elements, right? So we need to find the top k frequent elements. Okay, so here 1 is coming 3 times, 2 is coming 2 times, 3 is coming 1 time, right? And we need to return top 2 frequent elements. So what can we do? Top 2 frequent elements are 1 and 2, got it? Because it's coming 3 times and it's coming 2 times, right? So we need to maintain a priority queue. Okay, priority queue, we can maintain min heap, right, as we did in the last question, right? So again, on which either key or value, on which parameter we need to apply this min heap. So we will do what? We will store frequency. See, frequency is there. For frequency we will obviously use hashmap, right? Hashmap will be there, and we will be storing values, their frequencies as the key, these as the the element as the key, their value, their frequency as the value, correct? So we will be applying min heap on these values, right? So we will be storing these values. So in the heap, and again maintain the window, right? Window of size k, right? Okay, so first we will add 3, right? We will add 3, then we will add 2, but we need to maintain the order, right? So after this order will be, let's write it here, 2 will come first, then 3, right? So currently window is of k size, right? Then we will add this 1 is added. Now we need to maintain the window, so 1 should come at the first, right? Because this is the minimum, right? And we need to maintain the window of size k. We will return we will pop the element, so we will remove this element, correct? Now window is there of size k, elements are over, so we can say these are the elements, right? These are the elements with top k frequency, right? So these are the elements, correct? We are maintaining the window of frequencies, right? So at the last we will get top k frequencies, and we need to return the elements, so we can simply get their key and we will return the keys, correct? K minus 1 say start. Let me check in the question first. We need to return 1 and 2. Okay, let's update this answer. So we will be pushing values and 1 1 1 2 2 then 3, right? So first we will be using map. Okay, key will be and values 1, it's 3 for 2, it's 2 for 3, it's 1, right? After that we will be using priority queue, the min heap on the values, right? But we will be storing keys only on this priority queue. Got it? So in this method we will be calling what? We will be comparing these values, okay, but we will be storing keys only. Got it? How we can do this? So let me write it. Priority queue of type integer, pq, let's say, equal to new priority queue now. Here we will be passing the function. That means we need to compare a and b. We will be using lambda expression. We will be calling the comparator with integer, and we will be calling this function integer dot compare. Okay, now here in this we will be comparing the values for these, right? So in the priority queue we will be adding these keys only, and we will be comparing their values. That means map dot get a comma map dot get b. Got it? So what we are doing here, simply we will be like, we are we are adding this one, okay, in the priority queue, added. After that we are coming to 2. We are coming to 2. Now it will compare their values, right? A and b, we are passing it in the comparator, and we are comparing it. We are comparing their values, right? These are the values. Understood? Oh, so here what we are doing, let's say this is the function. How it is returning, like in the minimum order, like min heap or ascending order, we can say. How? See, we are giving basically ab as the parameter for the comparator. In that it's calling this integer dot compare method, where we are checking map dot get a means their values, right? And map dot get b, their values. For a it's 3, right? 3, and for b it's 2, right? Let's say we are comparing 1 and 2, right? So now it will return, if a is less than b, it will return 1 minus 1, this function, compare function. If a is greater than b, then it will return 1. If a equal to b, it will return 0, right? So in this case we are giving 1 and 2, we are having 3 and 4, that is 3 is this case, right? This case. So we can say what? b is smaller, so order should be 2 then 3, right? If it's 1, correct? That means b has higher priority. So b should come first, okay? And if we want to like get the max heap, then we can simply swap these values. B will come first and a will come after this b, okay? So that will return the max, the descending order. And in this, a has higher priority, a should come first, okay? It's important. So let's code it down. So what we are having, initially we are having the hash map, right, of type integer and integer, right? Let's say a map equal to new hash map, correct? After that we are having the priority queue, or before that let's put all the elements in this num we can use, or let's use I equal to 0, I less than nums dot length and I plus plus. So map dot put, here we will be using get or default method, right? Nums of I map dot get or default what? For nums of I we will take the value if it's present, otherwise we will take 0 and we will do +1, right? We are increasing the frequency. whenever we are getting the same element, correct? So by this we will be getting the frequency map. After that, priority queue, tq of type integer, right? pq, let's say, equal to new priority queue. Here we will be using comparator, right? A and B lambda function. After that, integer dot compare. What we need to compare? Map dot get A, right? Their values, their frequency. Map dot get B, right? So we are having the priority queue, in that we will be passing the key, but we are comparing them on the basis of their value, that means the frequency. Okay, and I explained how this function will return -1 and 1 and 0, right? So on the basis of that we will get to know the priority of A and B, and accordingly it will sort. Okay, so after that we will be having for loop on what? On this key set, right? Map dot key set, right? Now we will be pushing the keys in this priority queue. Dot what? Offer or add we can use here, val. After that we need to check the window also, right? So if pq dot size, see, after this everything will be same as I explained here, right? The only difference is we are storing keys instead of values. Okay, if the size of priority queue is greater than k at any point, then we will do what? We will remove the first element, right? That will be the smallest. Remove smallest element, and here we are using min heap on values, frequencies. Okay, so the topmost element will be the minimum element, right? So that's it. After that we just need to extract, right? As we need to return the array. So what we will do? First let's make the resultant result equal to new int of size k, right? Then use the int array. Now we need to add these elements, the remaining elements, in the array, right? Int array or the resultant. Okay, so let's say we are starting from the last. Okay, and I should be greater than or equal to 0 and I minus, correct? We are doing reversal. So result of I will be equal to pq dot poll, correct? After that we can return this result. Okay, let's run this. Accepted. Let's submit this. So it's accepted, right? The time complexity for this will be O n into log k. See what we are doing? We are having this for loop, right? This will go to O n time complexity, right? After that we are adding the element in the priority queue. Now this add function will take what? It will take O log the size of priority queue, that is k, right? We are maintaining k size, so the maximum number of elements will be k, correct? So the time complexity for this will be log k for this adding function, right? And for this removing, again it will be log k, correct? I explained this part, the height of the tree, correct? So overall it will be n into log k. Okay, so let's move to the next question. kth smallest element in a sorted matrix. Okay, so we are given the matrix, we need to find the smallest element. Okay, kth smallest element. Let's copy this. So we are given this matrix, that is 1, 5, 9, 10, 11, 13, 12, 13 and 15. We need to find the kth number, kth or kth smallest. Okay, kth smallest number. Okay, after sorting it will be 1, 5, 9, 10, 11, 12, 13, 13 and 15, right? The first way is extract all the elements from this matrix, make a matrix of size n into n, make a array of size n into n, right? And store all the elements, sort it and get the kth element, correct? This is one of the step, right? It will take space of n into n, time complexity of n log n, right? This is not the optimized way, right? And interviewer also may not be happy with this, because if we are asked to find kth, then they may are asking about priority queue. Okay, so how can we apply priority queue on this matrix? We need to find the kth smallest element, right? Now we need to find smallest, not largest. How can we find? We will simply traverse this matrix, right, using nested loop, for loop, inside for loop. Then we will store all the elements in this max heap, right? And side by side we will maintain the window of k size. Now here in this window all elements will be the smallest, right? Because this is the max heap. Let's say we are having the elements like 5, then 1, then 9, then 11, then 2. Let's say these are the elements. Okay, so in the max heap is there, right? So in the max heap, first we will insert 5, right? Inserted. After that we need to maintain the size of, let's say 2, here k is 2, so window of k size is maintained here. So after that we will insert 1. Order is maintained, yes, it's maintained. The largest element is at the top, we can return it first. After that we will insert 9. Now order is not maintained, right? 9 should come in the starting because this is the largest, correct? So 9 is at the front now. Now we need to maintain the window of size 2, right? But current window is size 3. We will remove the element, we will remove 9. We will remove 9 from the front. Okay, so the size of 2 is maintained. We will insert 11, right? Again order is not maintained, it will come in the first, 11 at the first. We will maintain the window, remove 11, window of size 2 is maintained, correct? After that 2. Now order is maintained, no, it should come in the middle, 1, then 2, then 5, correct? Again window is not maintained, we will remove 5, correct? At the last, window of size 2 is maintained with the smallest elements. And what is the kth? What is the kth smallest element? It will be the peak element, right? The peak element will be the kth, smallest element. Got it, guys? The same thing we are doing in the last question for the largest, here we are doing for the smallest. Understood, everyone? Yes or no? Okay, so here he is calculating time complexity. Great, it's correct. Yes, m is not there, it's n by n only, but it's correct. Okay, so we can simply use nested for loop and we can insert in the In the priority queue, what we need to insert? This nums of I and j, right? And after that we need to check the window, right? If pq.size is greater than k at any point, we will remove the last element, the first element basically. That will be the largest dot pool. Got it? That's it, the simple code. Okay, let's code it. So the priority queue will be there, priority queue of what type? Integer, right? After that name will be pq. It's basically Max Heap. Let's write it Max Heap. New priority queue. Correct. Now here we need to reverse the order, right? So collections dot reverse order. Correct. We will get the Max Heap. Okay. After that we will get the size, that is matrix dot length. Correct. That will be n by n, right? N by n matrix is there. After that we will be having first loop for int I equal to 0, I less than n, I plus plus. Second loop will be there from I j equal to 0, j less than n, j plus plus, and then we will simply add the dot add matrix of what I and j in the priority queue. Then we will check the size. If pq dot size is greater than k at any point, we will remove the element from the front, that means the largest element, because this is the Max Heap. So pq dot poll. Correct. That's it. After that we will return the pq dot peak. That will be the kth smallest element. Let's run this. Compilation error pq. Okay, I am using Max Heap. Accepted. Let's submit this. Okay, accepted guys. Time complexity will be n into n log k. Correct.